Hello and welcome. Today I'd like to show you how we can use our ZNB3000 network analyzer to perform two-tone intermodulation measurements on an active device. Here we have a small signal USB powered amplifier, which we'll use as part of the demonstration. And we're feeding the two tones that are coming from port 1 and port 3, which have separate signal generators behind, in through an external combiner to provide the two-tone stimulus into the amplifier. Let's start by setting up the frequency of the measurement on the network analyzer. Start frequency will be 100 megahertz, and stop frequency will be 3 gigahertz. We'll power the amplifier up and just check that we have some gain. Rescale the diagram, and here we can see we've got about 16 dBs of gain. Not calibrated, so we've got some loss through the splitter there. So we were expecting about 20, so that looks good. So now we can move on and configure the intermodulation measurement. In the measurement menu, from the drop-down menu at the top, where we have S parameters, we can select intermodulation. And we have a dedicated wizard in here that allows us to define the necessary criteria to perform the measurement. In the diagram, we can see this represents a setup that we have here in front of us. So port 1 is providing the lower tone, port 3 is providing the upper tone, and then we have an external combiner here that brings those two signals together. So we have the two-tone stimulus into the device under test, and then the received measurement is going back through into port 2. We can define what intermodulation orders we want to see. Normally, we're only interested in third-order products, but we can, of course, choose higher order products if necessary. And all this really does is if I just select those and choose next, it just extends the frequency plan of which the calibration and the overall measurement will be conducted over. So here, this went from the lower IM9 product, which is 96 megahertz, and the upper, through to 3.005 gigahertz for the higher end. If I go back and deselect these and choose next, then we have 99 megahertz and 3002 gigahertz. So what you can see here is that we have our lower tone, say F1, and then the upper tone F2. And from the definition, the third order lower product would be twice the lower frequency, so 2 times 100 megahertz, minus the upper frequency, F2, which is 101. So that gives us the 99 megahertz for the starting frequency. And then the upper third order product is twice the upper tone. So that's 101 megahertz times 2, minus the lower tone, which is the 100 megahertz. And that brings us then 102 megahertz. So that's our starting frequency for our two tones. And then the measurement will then sweep that across the whole range, all the way up to 3 gigahertz, and then give us the corresponding measurement results. We can also change the tone distance. So at the moment, we're just using the default 1 megahertz, but of course you can choose a separation that's relevant for your measurement. So with all of that set correctly, we can then choose next. And what I'm going to do here, we have all the different measurement parameters available. I'm going to start with just looking for a reference for the lower tone in, an upper tone in, and then lower tone out and upper tone out, just so we can get confidence that everything's working okay with our setup. So we'll choose next. And the final step of this is performing the calibration. Now for the intermodulation measurement, because we're not looking at S parameters, we can just perform a scalar power calibration. So we only need the USB power meter as part of this process. So we'll select continue with power calibration and finish, and that would take us directly into the calibration dialog. So I'm going to disconnect the amplifier now and connect the USB power sensor. Okay, so now we've connected the USB power sensor. We'll run through the first part of the calibration. And what this will do, it will calibrate the lower tone using the measurement derived from the power sensor, but then in addition, perform a flatness cal. So you'll see that will run through in one continuous sequence. It's pretty fast. So there's the measurement from the power sensor. It will get to the end, and then it will put limit lines on to ensure that the power flatness across the frequency band is achieved. and that took a second or so. Now it's running through calibrating the second tone or the upper tone, and then it will do the power flatness. And now that's the power calibration part complete. We disconnect the power sensor and we connect the combiner all the way through to port 2 to calibrate the receiver path back into the network analyzer. So for this final step, we simply have the power calibrated source at the end of the splitter combiner going into port 1. That takes almost no time at all, and now the whole calibration process is complete. We'll hit apply, and now we're ready to reconnect the device under test. So with the RF connections to the amplifier under test now made, we can power this up. And hopefully we can see the traces move off. I'm going to just reformat the scaling on these traces here so we can see exactly what we have. And one easy way to quickly do this, if I go to Trace Manager, because I want all the traces to have the same scaling, we can just couple trace 2, trace 3, and trace 4 to the scale of trace 1. And then when I reposition this one, they will all follow suit. And here we go. And then the last bit, I'm just going to couple the markers. And so what we see now are the orange and the green trace along the bottom. That's the minus 10 dBm. So that's the input power that I've calibrated into my amplifier under test. And the blue and the red trace are the amplified levels going back into port 2. So we can see those have a value of around about 10 dBm. So we're close to the 20 dB gain that we expect for this amplifier. Now what we can do is add our intermodulation products. So back in the intermodulation dialog, when we press measurement, we can see that if we select measurements here, I have a whole range of different products that I can add in as a trace quantity. So I'm going to select the lower IM3 product and we place that down to the bottom. And then also the upper IM3 product, and we'll overlay that into the bottom as well. And maybe also you don't just want to see the intermodulation products, but from those levels you can calculate what the intercept point would be, assuming the device didn't hit saturation. So this is the IP3 product at the output, and we can see that here as a calculated trace and put that on the top diagram. And I'll just reformat that. So now what we've got is intercept point on the top right and intermodulation at lower and upper on the bottom. Now with any of these active device measurements, we need to be absolutely sure what we measure is coming from the device under test and not coming from any nonlinearities in our receiver. If my network analyzer has step attenuators built into the receiver on the port, then in the power menu, I will see those here. This particular one does not, but I've already verified that what I see here is coming from the device and not from the receiver. I could, if necessary, add external attenuation and calibrate that out if necessary. It's pretty easy to come back into the measurement menu where you have the intermodulation power cal, which we've already been through. I can select this dialog once more, skip the power meter part. So I'll just say next, next, and the bit where you calibrate port 2, I could then do another measurement or calibration with an attenuator in at port 2, and then just check to make sure my intermodulation products have not changed. If they have changed, then we know it's coming from the network analyzer and not from the device under test. So let's just cancel that. Another thing that is nice to look at is once we've got our measurement, so we can see our intermodulation products at this frequency, 1.55 gigahertz, are around about 32 dBm. It's nice to be able to play around with the power level and see effectively where maybe your best linearity might be. If you're designing an amplifier for a certain kind of communication system, then these are important parameters. I'm going to change the step size here to 1 dB per. And now, if I just move that off of here, so we're at 10 dBm at the moment. I'll use a thumb wheel and I can just change the stimulus level into the device under test and monitor how the intermodulation products behave with the varying input level across the frequency band. So that's quite a nice little test to do. Then once I've found the optimum level, I'm going to stick with the minus 10 dBm here, then I've got all the information that I need. One last thing that we can do, if I go back to the measurement menu, where we're in the intermodulation dialog, right down at the bottom is this button that says Add CW Mode. If I just select that, actually before I do, underneath that, you can choose the order of intermodulation products that you want the CW mode to span over. So let's just say 7 in this case. I'll add that, and that'll add a CW mode trace. It's always nice to drag that into a different diagram because the bottom axis is different now, because what we've got is all these other traces have swept frequency, and this one here is effectively looking at a spot frequency in terms of stimulus and then looking at the swept spectrum. So what we can see if we just zoom in, just rescale that slightly. Let's put some markers on here. Marker 2, search, max, next peak. So there's my F1, F2 stimulus feeding into the amplifier. And then we'll look at the third order products. We can go to marker 3, search. And then finally, we'll add a fourth marker, max, next. So there's my lower IM3 product on the left-hand side at marker 3, my upper IM3 product at marker 4. And just to make sure that this all looks good, you can see on this diagram, they're at 32 dBm at a specific frequency of 1.55 gigahertz. And if we go to the swept measurement at 1.55 gigahertz, my markers there are 32 dBm. So the two correlate. So now you can see we can easily display all the measurement quantities that are necessary for characterizing the two-tone intermodulation products on an amplifier like we have here. Hopefully you can see that the ZNB3000 makes this process easy. If you need any more information, please go to our website where there's loads more videos and content that will make your life much easier.